So in this talk, I will tell you about the complexity of computing KKT solutions of quadratic programs. So what is a quadratic program? A quadratic program is a very simple and standard optimization problem of the following form. You have an objective function that is a quadratic polynomial and just simple linear constraints. So for example, a program of this form would be a quadratic program because the objective function only consists of terms that have degree at most 2. So this term, has degree 2. This term has degree 2 as well. This one has degree 1. And the constraints are just simple linear constraints. So what do we know about this very standard type of optimization problem? Some special cases first. If this matrix Q happens to be 0, which means that essentially there are no quadratic terms in the objective function. In other words, the objective function is linear, and in that case, this is just an LP. And so we know that this is easy to solve. It can be solved in polynomial time. Another special case, which is a generalization of this first one, is when the matrix Q is a positive semi-definite. In that case, it turns out that the objective function is convex. And again, for that case, convex optimization can be solved efficiently. So in general, there's no guarantee about the matrix Q. And unfortunately, problem is known to be NP-hard when the matrix Q does not have to be necessarily positive semi-definite. Now, the importance of quadratic programming comes from the fact that it can capture many important problems. So it is very powerful in terms of what it can be expressed as a quadratic program. And so perhaps it's not surprising then that the problem in general is NP-hard. So let's take a brief look at one way to show NP-hardness by showing how we can express a very basic problem such as max cut, which is known to be NP-hard, how we can express that as a quadratic program. So in the max cut problem, we're given a graph, and the goal is to partition the vertices into 2 groups, let's say red and blue, and to maximize the value of the cut that this partition creates. So the cut is the edges that cross from one color to the other one. In this case, all the yellow edges would be the cut edges, and want to maximize the number of such edges. So the value of this particular cut would be 5 because there are 5 edges crossing. And the general goal in this problem is to find a partition that maximizes the value of the crossing edges, the number of crossing edges. So this problem is known to be NP-hard, and it's not too hard to express it as a quadratic program. So this is one way to do it. So we have an objective function which is quadratic, and we have these variables xi, where xi lies between -1 and 1, and we think of the value being 1 as representing when it's on the blue side, say, and when xi is -1, then the ith vertex is on the red side. And then it's not hard to see that when these variables xi take the value 1 - 1 to encode the side on which they lie, that this objective function, which is quadratic, exactly expresses the value of the cut. And now if we have a solution of this quadratic optimization problem, it's also not too hard to see because of the particular form of the objective function, which is multilinear, that we can easily round it so that the variables are all -1 or 1, so no values in between, and that they will exactly correspond to a maximum cut. So this is just one example of how you can express a problem as a quadratic program, and there are many more. And so it's not surprising that the problem is, in general, NP-hard. So given this NP-hardness for finding a global solution, a global minimum or global maximum in this case, of a quadratic program, it is very natural to ask or to consider relaxations of this solution concept. So to ask for something that is maybe not a global minimum, but still some reasonable solution. And so perhaps the most natural relaxation to consider is a local minimum. In other words, a point such that in its immediate vicinity, there is no other point that has a lower value than the current point. So it's locally, it's minimal. So unfortunately, it's known that even just verifying whether a point is a local minimum is actually, perhaps a bit surprisingly, NP hard for these quadratic programs. And more generally, finding such points turns out, and this was only proved quite recently, to also be NP hard, so just as hard as finding a global minimum of the function. So another relaxation that we can then look on, which is a further relaxation of a local minimum, is a so-called stationary point. And this is what we're going to focus on in this talk. More formally, we're going to consider what is called Karush-Kuhn-Tucker, KKT points. And these are points where essentially based on the first order information, so the gradient of the function, the point is a local minimum. So what do I mean by that? Let me define it. So intuitively, you should think of these KKT points as being fixed points of gradient descent. In other words, points where if you were to start running the gradient descent algorithm, let's say one step of it, you wouldn't move, you would stay, you would remain at the current point. And this is not only correct intuitively, it's actually correct also as a formal definition. But let's look at an example in one dimension to see what these points correspond to. So here I have a function in one dimension. This is not a quadratic polynomial, but it doesn't matter to define the notion. So our domain is just the 0, 1 interval, and we have this nice smooth function f. So what is the global minimum of this function? It's this red point. What are local minima of the function? Well, this point, as well as the original global minimum, this point here as well. These points up here are local maxima. And now I claim that all of the points that I've drawn up here, they are all also KKT points. So the KKT point is really a relaxation of global optimum and of local optimum. And the reason is that the gradient at all of these points is 0. So if you were to start at one of those points and run gradient descent, you wouldn't move, you wouldn't go anywhere. Okay, so for this reason, all of these points are valid KKT points. In fact, this function has one more KKT point, namely the point over here. And the reason is that although the gradient is not 0 here, because our domain is just a 0, 1 interval, if we were to do gradient descent starting at this point, we would move towards the left, but that's the end of the domain. So we would be projected back onto the domain and we'd stay where we started. So for that reason, this point here is also a KKT point. And now the picture is complete. These are all the KKT points that we have. So it's clear from this example that KKT points is a significant relaxation of local minimum. There are many more of them. And so we could hope to, compute KKT points more efficiently than we can for the other points, for local minima, let's say, which are NP hard. Let me briefly touch on what happens in higher dimension. So in general, what is a KKT point? If the point lies inside the domain, it's a point where the gradient is 0. If the point lies on the boundary of the domain, then it's a point where if we take minus direction of the gradient and then project back onto the domain, we end up again at the point where we started. Okay, this is a formally correct definition of what a KKT point is. Before we start looking at the complexity of computing these KKT points, it's very natural to ask ourselves, is this a reasonable relaxation? Why should we study this particular relaxation, not look for some other solution concept? So one first thing that is very nice about the solution concept is that it's easy to verify whether a given point is a KKT point or not. Indeed, we just need to run one single step of gradient descent and see whether we moved from our original point or not. So that can be easily done in polynomial time. A second motivation is that as I introduce KKT points, they are indeed just fixed points of gradient descent. In other words, the solution towards which gradient descent ultimately converges. And so given the importance of the gradient descent algorithm, understanding the complexity of finding these gradient descent solutions is very natural. Another interesting observation is that, as I mentioned earlier, complex optimization is easy, can be solved efficiently. And it just so happens that in that case, in the complex case, the KKT points coincide with the global optima. They're the same thing. And so one might wonder whether the fact that convex optimization is easy is just a consequence of the fact that maybe finding KKT points is easy in general. And in the convex case, it just happens to be that those are also the global solutions. So it's very natural to ask, could it be that these KKT points can be found efficiently in general, also in the non-convex case? The question also of studying this particular problem, so the complexity of finding KKT points in quadratic programs, is, it's very natural. So it was already asked explicitly in the 90s. And finally, although this is a relaxation of what we usually want, which is a global optimum, for some applications, so for some problems that can be formulated as quadratic programs, it turns out that finding these KKT points of the quadratic program is actually enough. It's all we need. So in particular, I give here one example, the problem of finding a mixed Nash equilibrium in a particular type of game, which is called a network coordination game. So this can be formulated as a quadratic program, and it turns out that it suffices to find a KKT point of that quadratic program to get a Nash equilibrium. You don't need to find a global optimum. So for some applications, KKT points are actually the solution concept that we care about. So this leads us to the natural question: what is the complexity of computing a KKT point of a quadratic program? And the first thing to try out is, well, since KKT points are just fixed points of gradient descent, what about just running gradient descent? Gradient descent is indeed guaranteed to converge to a KKT point, but is it an efficient algorithm? The answer is no, this is not an efficient algorithm. And the reason is that it finds an approximate an epsilon KKT point in time polynomial in 1 over epsilon. So if you're looking for a high accuracy or exact solution, this is not going to be efficient. Epsilon is going to be exponentially small, and this is going to be, the running time is going to be exponentially large. So for example, for convex optimization problems, they can be solved efficiently in poly log 1 over epsilon. And that is exactly what we would consider efficient here as well. Gradient descent does not satisfy this. Okay, so gradient descent doesn't work. So maybe the problem is just NP hard, just like the other solution concepts were global optima and local optima. So it turns out that here NP hardness is actually not really an option. And the reason is that the problem cannot be NP hard unless something very surprising that we don't expect to hold happens, namely that NP equals co-NP. And the reason for that, very briefly, is that the problem is a so-called total NP search problem. So it lies in the class TFNP. These problems have two crucial properties. First of all, solutions can be verified in polynomial time. And secondly, a solution is always guaranteed to exist. And our KKT problem has both of these properties. First of all, as I mentioned earlier, we can easily verify if a point is a KKT point or not. And secondly, a KKT point is guaranteed to exist because we consider, a bounded domain. So in particular, a global optimum has to exist, and a global optimum has to be a KKT point. So we have both of these things. Our problem lies in this class TFNP, and it is known for this class that the problems cannot be NP hard unless this very surprising thing holds. So NP hardness is not an option. What can we do? How do we provide evidence that some TFNP problem cannot be solved in polynomial time? So it turns out that there are various intermediate classes, so classes inside TFNP, that can be used to classify TFNP problems and to provide evidence that there is no polynomial time algorithm. So you might have heard of some of them. So PPAD is quite well known because it exactly captures the complexity of computing Nash equilibria in general games. PLS is known to exactly capture the complexity of computing a locally optimal solution for max cut, as opposed to a globally optimal solution that we considered in the example earlier. If you define some sort of a local solution, then this turns out to be PLS complete. And our problem of interest here, so finding KKT points of quadratic programs, turns out that this problem lies in the class CLS. And so it is very natural to try to prove that it is CLS complete, because that would give very strong evidence that the problem does not admit a polynomial time algorithm. So what do we know about computing KKT points more generally? If we allow the function the objective function to be more general than quadratic, then we know that the problem is CLS complete for some cases. So if the function is given by some general type of arithmetic circuit, for example, then we showed a few years ago that the problem is indeed CLS complete in that case. And Babichenko-Rubinstein a bit later also showed that if f is an explicitly given polynomial of degree 5, again, the problem remains CLS complete. So we can reformulate our question as asking, do these hardness results still hold if now our function is the simplest non-linear objective function, namely it's just a quadratic polynomial. And the main result of our work is that, yes, the problem remains just as hard. It's CLS hard, CLS complete in the quadratic programming case. So if the objective function is just a quadratic polynomial, and our hardness result holds even for the simplest box constraints. So we just assume that the constraints are just that x lies in the standard unit box. So in the rest of this talk, I will give a very, very brief overview of how we prove this, very high level. And then I'll mention some open questions. So as I mentioned, we know that the problem is hard if the objective function is more general, if it's represented by a circuit. So our general idea is going to be to reduce from the version with a circuit to a problem where the objective function is just a quadratic polynomial. And as a toy example, let's consider the circuit here that we have on the left. So it has two inputs, x1, x2. It has one gate computing the sum of the two, and then another gate multiplying the output by -2, and this is then the output of the circuit. So this function just computes, this circuit just computes the very simple function f, capital F down here. So what we show as a first step is that you can write down a quadratic polynomial that actually encodes this circuit. So how do you do that? You're going to add essentially one term for each gate of the circuit. So the first gate of the circuit just does the sum of those two inputs. And so we're going to add a first term here. We're going to ask essentially because we're minimizing, to make this term small, which is going to force x3 to be close to the sum of x1 and x2. Similarly, for the second gate, we're going to add another term. And we will add that term with a small weight delta to essentially let the variable x3 know that this term is more important for x3 than this term, because this term is telling x3 what value it should take. And so you can do this similar for all the gates. In this case, we only have those two. And at the end, you add one more term, which is going to be the output of the circuit. In this case, it's the variable x4. And so what we show, and I'm not going to go over the details, but it turns out that you can show quite easily that the following holds. If you have a KKT point of this quadratic polynomial, then that point has to be an approximate KKT point of the function represented by the original circuit. Okay, we call this the backpropagation lemma, because essentially it turns out that the errors introduced by this last term propagate up the circuit and exactly compute the gradient of the original function, and you get this nice connection. So this is not too hard to show. The question then is, how exactly do we use this? So the first complication is that this only works with these simple linear affine gates that we had on the previous slide. And the problem is that the problem of finding KKT point of such a circuit that only consists of such gates is easy. Okay, so we need to introduce more complicated gates. A very natural type of gate to introduce is a multiplication gate. Unfortunately, this is not going to work because if you add a term that does multiplication, you get a polynomial that has degree 4 already. So the degree is too high. Instead, it turns out we can use the fact that we have this boundary on the variables lie between 0 and 1, to implement some kind of a linear truncated gate. So there's a linear affine function, and then there's a truncation that truncates the value to lie between 0 and 1. And so we can implement these gates. This nice lemma, though, this backpropagation lemma, unfortunately fails for this case, and we instead have to prove some kind of a perturbed version of the lemma. And then in order for the reduction to yield CLS hardness, we have to show that it is CLS hard to find a KKT point of this type of circuit that consists of this gate. And in fact, to find KKT point even if we perturb the circuit a bit, even if we're allowed to perturb the circuit to help us find KKT points easier. So the details are quite technical, but this is the high level idea behind the proof. So let me finish by mentioning some open problems. So the first one is that we would like to show a hardness for the case where the objective function is multilinear. So there's no quadratic terms like x1 squared, but only we allow x1 times x2 terms, etc. Because that would imply, if we prove this with the same domain, this box, unit box domain, that would imply hardness for one of the motivating problems, namely this network coordination game that I mentioned. So that is one very interesting direction that seems quite challenging. Another general direction is to consider other natural domains. For example, what if the domain is the simplex? We don't know of a simple way to extend a result to that setting. And finally, our reduction heavily relies on these decreasing weights with the deltas. And so we don't know what the complexity of the problem is if we restrict the coefficients of our polynomial to be not too large, so to be given in unary. So we don't know whether a positive result is possible or if there's some other way to prove a hardness result. And so that's all I wanted to tell you about. Please feel free to contact me or any of my co-authors if you have any questions. Thank you.